Hello future engineers, welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. That's one way you can keep me going, inspired and refreshed. Now, if you find my videos interesting and important to your studies, also please don't forget to subscribe. In this video, we will discuss the representation of a force, a 3D force especially, into rectangular components, and we will also resolve a 3D force into its x, y, and z components by purely computing the components of a force based on the magnitude and the angles it makes with the coordinate axis, namely x, y, and z, or in terms of the component of distance and the distance where the force is directed to. So I hope that you can follow my explanation, and I tried my best to make it simple to follow, although it also needs your mathematical background. So here it is. So we have x, y, z coordinate system, the Cartesian coordinate system, which are mutually perpendicular to each other, and a force is directed. Let's consider first a force which is directed from the origin. The starting point is the origin to any point. The terminal point has coordinates x, y, and z. And this force is directed along the diagonal of this imaginary box. So therefore, the diagonal of the box is the longest. And we conclude also that the magnitude of the force is highest because it is longest. So the components of the force are namely Fx, Fy, and Fz. And this force makes an angle of theta x with the x-axis. So these are the dimensions actually of this imaginary box. Actually, x is x terminal minus x starting x, which is the origin, so 0. So that's just x. Y minus yo is 0. So y minus 0 equals y, and z minus 0 is z. And this f makes an angle with respect to the x, y, and z, respectively, of theta x, theta y, and theta z, respectively. These theta x, theta y, and theta z are called direction angles, and their cosines are called direction cosines. So the x component of the force is from origin along the x-axis. So that is Fx. By the way, the length of the diagonal where the force is directed to is denoted by d, and this d is simply square root of x squared plus y squared plus z squared. So this Fx forms an angle with the diagonal of this wall here, which is vertical, an angle of 90 degrees. So to show that, just imagine a rectangular folder, and you're going to rotate one surface of the folder forward, and the angle remains 90 degrees, such as this. So that's why this angle is also 90 degrees. So actually, it is this rectangle here that is inclined. So I hope that you can imagine. So that's why this angle here is also 90 degrees. So therefore, this triangle is a right triangle. So we can now define cosine of theta x, which is adjacent side fx divided by f. And in terms of the dimensions, it is equal to x over d. So cosine theta x is fx over f. And cosine theta x in terms of the dimensions would be x over d. So equating cosine theta x, so we have fx over f equals x over d, and we interchange position between f and x, so that fx over x equals f over d, so that you can easily recall these equal ratios as x component of force as to x component of distance equals the force divided by the distance where the force is directed to. So likewise, we next defined cosine theta y, but before that we have to form or show Fy. So obviously, Another right triangle is formed because this is vertical and this is the horizontal diagonal on the ceiling. So remember, the angle between the horizontal line and the vertical is 90 degrees. So that's why it's also 90 degrees there. So defining cosine theta y, which is equal to Fy over F, the hypotenuse. And in terms of distance, cosine theta y is equal to y, because this is y, equal to this, over d. So y over d. So equating cosine theta y, we have Fy over F equals y over d. Then again, we interchange position between F and Y so that we can easily recall the equal ratio as Fy, or Y component of force, as to Y component of distance equals the force over distance. Then finally, the line joining the tip of the force to this corner here will again form an angle with this z-axis, an angle of 90 degrees, because this is vertical line, this diagonal is on the vertical wall, and OZ, or the z-axis, is horizontal. So the angle there is 90 degrees. Or by deductive reasoning, cosine theta z equals Fz over F, and it is also equal to z distance over d. So again, equating cosine theta z, so we have Fz over F equals z over d, and interchanging the position of F and z, so Fz, z component of force, divided by z component of distance equals force over distance. Now we form these 6 ratios, and we write them as one, as Fx over x equals Fy over y equals Fz over z equals F over d, or simply the force multiplier. So the ratio of the force to the distance where that force is directed to is called force multiplier. And we form these equal ratios. Remember, it's easily remembered. We can easily remember this because it is simply x component of force divided by x component of distance equals y component of force equals, as to y component of distance equals z component of force, as to z component of distance equals the force, as to the distance of that force equals force multiplier. So I hope you can remember that easily. So of course, the x component of force from this ratio is equal to the magnitude of the force times x component of distance divided by distance. And remember, x component of distance divided by distance is cosine of theta x. So therefore, the x component of the force is simply the magnitude of the force times the x component of distance divided by distance. Or simply force multiplier times x, or x component of distance times force multiplier, or f cosine of theta x. From here, it is hypotenuse times cosine of theta x. Fy is hypotenuse f times cosine of theta y. Fz is hypotenuse f times cosine of theta z, so that we can easily remember this x component. Y component is equal to magnitude of the force times y component of distance over distance, or f cosine theta y. Fz is f z over d, or f cosine of theta z. So I hope you can easily remember that. Or simply component of distance times force multiplier. That's the component of a force along x, y, and z. So magnitude of the force times x component of distance divided by d. That's the x component of force. The y component is f y over d, or simply f cosine theta y, and the z component is magnitude of the force, z component of distance divided by distance, or simply f cosine of theta z. So if the force is directed from point S, the starting point of the force, that where the tail is located, with coordinates xs, ys, g sub s, to point T, the terminal point, so xt, yt, z sub t, the distance d can be written as we simply replace x by x terminal minus x starting quantity square, plus y terminal minus y starting quantity square, plus z terminal minus z starting quantity square. So the distance, the x, is simply replaced by x terminal minus x starting quantity square, plus y terminal minus y s starting square plus g sub t minus g sub s quantity square. So that's now the formula for that distance, or simply it's the diagonal of this imaginary box. So it is the square root of the sum of the squares of the perpendicular dimensions. So that's it, to easily recall it. So fx is f times xt minus xs. We simply replace x distance by this xt minus xs over d, where d is now changed by this formula. So it is still f cosine of theta x, even if the force is not directed from the origin to another point. It may be directed from point S to point T. Fy is magnitude of the force times quantity yt minus y sub s over d, or simply magnitude of force cosine of theta y. And Fz is magnitude of the force quantity z sub t minus z sub s over d, or simply f cosine of theta z. So it's still the same. So you better familiar with this general expression, because not all the time the force is directed from the origin. Then similarly, if we compute f in terms of its components, so remember this is a rectangle, so this is the diagonal or the hypotenuse of these two identical right triangles. So therefore, in terms of the components, this diagonal or resultant of fx and fz is square root of fx square plus fz square. Since this vertical component is fy, so we form another right triangle with a hypotenuse equal to the force F, and this angle here is 90 degrees, so that F square is the square of Fx square plus Fz square, square root of Fx square plus Fz square quantity square plus Fy square. So Fx square root of Fx square plus Fz square quantity square plus Fy square equals F square. So therefore, we can write that as Fx square plus Fy square plus Fz square equals F square. If we divide everything by F square and write it as Fx over F quantity square plus Fy over F quantity square plus Fz over F quantity square equals F over F quantity square, take note that Fx over F is cosine of theta x, F cosine of theta x, Fy over F is cosine of theta y, and Fz over F is cosine of theta z, and F over F quantity square is 1. So that the sum of the squares of the direction cosines is equal to unity 1. So again, cosine square of theta x plus cosine square of theta y plus cosine square of theta z equals 1. So if theta x equals theta y equals theta z equal to theta, then we can solve theta or the equal angle as 54.74 degrees, and that is computed because theta x, theta y, theta z are equal, so we can combine them and write them as 3 cosine square of theta equals 1. So therefore, theta is inverse cosine of 1 over square root of 3, and we will get 54.74 degrees, that equal angle there. So this is computed from this equation here when all these three angles are equal. So inverse cosine of 1 over square root of 3. That's 54.74 degrees. So in vector form, the resultant or the force is equal to uh, fxi plus fyj plus fzk, or simply magnitude of force. This is in vector form, it's boldface. Magnitude of force times quantity x component of distance, which is xt minus xs in general, plus y component of distance, which is yt minus ys, then times the unit vector j, then z component of distance, which is z sub t minus z sub s, times the unit vector along the z-axis divided by distance. So again, it may also be magnitude of force F over distance times quantity x component of distance I plus y component of distance j plus z component of distance k, where I, j, k are unit vectors along x, y, and z respectively, and the magnitude of the force is square root of fx square plus fy square plus fz square from the equation here. So all these are the principles and formulas that you will apply in the analysis of the following slides, which are devoted to problem solving. So I hope that you can recall the important principles, especially in computing the component of the force and the magnitude of the force, or simply the resultant. So our first step is to first practice resolving a 3D force into its components, so that once we master resolving a force into its components, then it's easy for us to compute the resultant of two or more 3D forces using the principle that the x component of the force is simply the sum of the forces along x. The y component of the force is the sum of the y components of all forces, concurrent forces. Then the z component of the force is the sum of the z components of all forces in the system, as long as they are concurrent. So we are now ready to solve sample problems in resolving a 3D force into its components. So here is the first problem. Resolve the force shown into x, y, and z components. So the force has a magnitude of 360 newtons, and let's describe its direction. It is directed up, to the right, and backward. So it is directed backward, or opposite to the z-axis, up and to the right. So therefore, we expect that the z component of this force is negative. So remember also that this shaded triangle is a right triangle because this is parallel to the y-axis, and this is a horizontal line on the xz plane. So the component along the xz plane, we'll call that fxz. So we will solve that first in order to solve for fx. Then once we solve for fxz from this right triangle, then we draw the x and z view, or we draw the top view showing the x and the z axis, so that we can analyze the x and the z components. So for the solution, so we have to solve for fxz first, this adjacent side of the right triangle, that's fxz. The opposite side is parallel to the y-axis, so that is the y component of the force. So by the way, theta y can be solved because the vertical angle of the force is 25 degrees. And remember that this horizontal line and this vertical line will form 90 degrees. So theta y is equal to 90 minus 25. So this is 65 degrees. So that Fy is, remember, magnitude of the force cosine of theta y. So cosine 65. Although the y component can also be written as 360 because it is opposite of 25 degrees. So it is hypotenuse 360 sine of 25, or 360 cosine of 65 degrees. But first, let's solve for fxz. So fxz is in this right triangle, it is equal to hypotenuse cosine of 25. It is adjacent to 25 degrees. So 360 cosine of 25 degrees, fxz is equal to 326.27 newtons. Then we draw the top view. So the x-axis, the z-axis, and fxz is in this direction here, making an angle of 20 degrees with the x-axis. So forming the right triangle, or the box, drawing lines parallel to the z and the x-axis, so that we can analyze fx. So this is fx here, and this is a right triangle again. So obviously fx is equal to fxz, the hypotenuse, which is 326.27 cosine of 20, and that is positive because it is directed towards the positive x-axis. So positive 326.27 fxz cosine of 20 degrees. So fx is equal to 306.6 newtons. So always finalize your answer, round off your answers to 4 significant figures. So that's 4 significant figures. Next, for Fy. So Fy is either 360 sine of 25 from this right triangle here, this is Fy, or 360 cosine of theta y, which is 65, 360 cosine 65. So Fy is 360 sine of 25 degrees, or it is also 360 cosine of theta y, or 360 cosine of 65. So Fy is also positive, 152.1 newtons. So it is only Fz that is expected negative because it is opposite to the positive z direction. And in this right triangle, it is hypotenuse Fxz sine of 20, but it is preceded with a negative sign. So opposite to 20 degrees. So Fxz negative 326.27, the negative sign is preceded because we anticipate that Fz is negative. Then times sine of 20 degrees. So Fz is negative 111.6 newtons. So that's it. These are the x, y, and z components of that force. So let's proceed to the second example. Resolve the 45 kilonewton force shown into x, y, and z components. So let's describe the force so that we can anticipate the components. It is directed forward along the z-axis, downward opposite to the y-axis, and rightward, so towards the positive x-axis. So forward, rightward, downward. So we expect that the y component of this force is negative. So again, this shaded triangle is a right triangle. This is also a right triangle. So we can compute first Fxz because this lies on the xz plane. So Fxz from this right triangle is equal to hypotenuse 45 cosine of 30. That is Fxz. So this is the top view. So that Fxz is shown. This is Fxz, which makes an angle of 40 degrees with the positive x-axis. So that's it. So that is Fx. So Fx is Fxz cosine of 40. But before Fx, we solve first Fxz, which is from this right triangle here, it is equal to hypotenuse 45 cosine of 30. That's Fxz in this right triangle. So 45 cosine 30 is equal to 38.971 kilonewtons. So having found Fxz, which is the hypotenuse of this right triangle here, then Fx is going to the right, going to the positive x-axis, it is positive. So Fx is 38.971 cosine of 40. So Fx is positive 29.85 kilonewtons. Next, Fy, this is Fy here. So it is going down. So using this right triangle, Fy is negative because it is going down opposite to the positive y-axis. It is the opposite of 30 degrees. Therefore, it is hypotenuse, which is 45 negative. Negative, the sign is negative. So negative of quantity 45 sine of 30 degrees, or 45 cosine of the angle that this force makes with the y-axis. Because this angle here is 30 degrees and the angle between the y and Fxz is 90 degrees. So the angle theta y is 90 plus 30, 120 degrees. So Fy is either negative of quantity 45 sine 30 or 45 magnitude of the force cosine of theta y, and theta y is 120 degrees. So negative 45 sine of 30 degrees, or it is 45 cosine of 120 degrees, where 120 degrees is again 90 degrees plus 30 degrees. 90 between y-axis and the xz plane, xz line or Fxz, that's 90 plus 30. So 120 degrees. So Fy is equal to negative 22.5 kilonewtons. Then having known Fy, we can now compute Fz, which is positive. This is the z component. And in this right triangle, it is the opposite to 40 degrees in this right triangle here. So it is positive. So it is Fxz, 38.971 times sine of 40, because it is opposite. So FZ is 38.971 times sine of 40 degrees. So FZ is equal to 25.05 kilonewtons. So that's it. So actually, we can check our work from example 1. You may check if square root of 306.6 square plus 152.1 square plus 111.6 square is equal to 360. So you will do that in your situation there. You just compute if it is equal. I already computed that and I already checked that. In this case, we can check square root of 29.85 square, fx square plus fy square plus fz square should be equal to f. And that is approximately equal to 45 kilonewtons. So that checks our answers. For our next example, problem 3, a 580 Newton force is directed from the origin to the point -3 meters, -2 meters, 5 meters. Resolve the force into its rectangular components. Also compute the direction angles. So for the solution, actually you may not draw the figure. We can easily answer this because the force is directed from the origin to the point. So the x component of distance -3, y component of distance -2, then the z component of distance is 5. We can compute the distance as square root of 3 square plus -3 quantity square plus -2 quantity square or plus 5 square. Actually, even if the distance is negative, as long as it starts from the origin, you may just consider them positive because anyway, they are still squared. But for the sake of their components, the x is negative y component and the z component, so we have to put the sign. So this is the point, starting point 0, 0, 0 meters and the terminal point -3, -2, comma 5 meters. Then we imagine a box with this force as the diagonal of the box so that we can easily describe the direction of the force. It is directed forward, so z component is positive, downward, so y component is positive, and leftward, so x component of force is negative. So that's why negative along x, negative along y, and positive along z. So the distance is square root of -3 minus 0 square plus quantity -2 minus 0 square plus 5 minus 0 square, or simply -3 square plus quantity -2 square plus 5 square. So that distance is equal to square root of 38 meters. And remember that the x component is magnitude of the force 580 times x component of distance -3 divided by distance. Or you may write that in this form. So magnitude of the force, delta x, x component of distance divided by distance. So Fx is equal to -282.3 newtons. Fy is magnitude of the force times yt minus ys over distance. So it is equal to 580 times quantity -2 minus 0 over square root of 38. So Fy is equal to -188.2 newtons. Then Fz is equal to F quantity z sub t minus z sub s over distance, where g sub t is 5, or simply collect this value inside the parentheses. So 580 times 5 minus 0 over square root of 38. So Fz is equal to 470.4 newtons. So these are the components of the force, x, y, and z components of the force. Now, if you want to check, remember you can check it, square root of fx square plus fy square plus fz square must be close to 580 newtons. For the direction angles, remember that fx is f cosine of theta x, or magnitude of the force cosine of the direction angle along x, or with respect to the x-axis. So -282.3 equals 580 cosine of theta x, or cosine theta x is equal to fx over f, or theta x is inverse cosine of fx over f. So theta x is 111.9 degrees. By the way, if the component of the force is negative, then the angle is more than 90 degrees. If it is positive, the angle would be, the direction angle would be acute angle. So Fy is F cosine theta y. So substitute. Again, Fy is negative. So we expect more than 90 degrees for theta y. So theta y inverse cosine of negative 188.2 over 580 is 108.9 degrees as expected. Then Fz is equal to magnitude of force cosine theta z. 470.4 is equal to 580 cosine of theta z. So theta z is inverse cosine of 470.4 over 580. So theta z is expected acute 35.8 degrees. So these are the direction angles. So we can check because we still have space here. So our first checking is the magnitude. So square root of fx square plus fy square plus fz square must be close to 580. So if using your calculator, that is around 580. So meaning our computed components are correct. Then for the second checking, we check that the sum of the squares of the direction cosines must be equal to unity or 1. So cosine square of 119.1 degrees plus cosine square of 108.9 degrees plus cosine square of 35.8 degrees. So using your calculator there, it is almost 1. So that checks our answers.